This device is a watt balance based on the Lego project. You can find more information about this by doing a Google search for Lego watt balance. The sites in the YouTube found in that search result are better explaining what this does, but briefly, it weighs something without reference to a mass standard such as the kilogram in Paris, which was used up until 2019. Every other weighing device until 2019 referenced back to this Paris kilogram. I will be covering the details of my implementation using wood instead of Legos. The coil is wound around an orange pill tube and slides over two magnets that are opposing each other so that the magnetic field lines radiate out horizontally. The same magnets and coil arrangement are at each end of the beam. The line laser at the top points at the wall about 222 inches away. I'll explain more on this later. It is used for calibration, not during a run. The position amplifier board helps measure the shadow of the line laser on the photodiode. Below the position amp is a 16-bit analog to digital converter, otherwise referred to in this document as ADC. It divides the 2mm movement of the coils by 64,000, which is about 30 nanometers, the length of a virus. I can't really measure a virus, there's too much noise, but we get to the bacteria size is what it can do. On the breadboard is an amplifier for the coil voltage from the coil on the left. When the coil speeds through the magnetic field lines, a voltage is produced based on the velocity, the coil, and the magnetic field. The coil on the right is a driving coil. It gets a 1.5 second sine wave from a function generator, which isn't visible. The little microcontroller board is an STM microcontroller, which goes by the name of Blue Pill, and they sell for about $8. It gets data from an external ADC and also its internal ADC, and remember ADC stands for analog to digital converter. I'll be using that abbreviation quite a bit. Well, anyway, the ADC sends the microcontroller sends its data to the USB dongle device. The other dongle, the red one, is used to program the STM32. It's not active except for providing power during the running. The system runs on 3 different sets of batteries due to various voltages used. The photodiode, which is the most expensive part, it's $100, is on the other side of the green circuit board. This view shows the details of the line laser that is pointing at the photodiode. The photodiode is really an expensive, tiny solar cell. The line laser vertical beam is blocked halfway along the photodiode. A foil strip acts as a knife edge to cast a shadow on the photodiode. The photodiode produces a voltage based on how much light it sees. It varies between 30 to 60 millivolts. Here's what is happening across the room about 222 inches away. This line laser beam is not part of a run. Instead, before a run is made, the driving coil is connected to a constant DC voltage, so the beam can be set into any desired angle, the balance beam, not the laser beam so much. The 5 points are taken: the upper red square, the lower red square, between the red square and the blue square, above the blue square, and at the upper red square. At each position in millimeters, the corresponding value from the analog to digital converter, ADC, is read. These values go into a spreadsheet to do a regression line calculation, which results in an intercept and slope, and those numbers go into the Python program. I'll show the results of that later on. In other words, for any given ADC value, I can know the position of the coil within a length of a bacteria cell. Remember, the coil is only moving up and down about 2 millimeters. Here's the display that's going to my notebook computer. The STM32 microcontroller sending data at 11,000 characters per second. This data is captured by a program called PuTTY and placed in a file for later processing by the Python program. The two values are the voltage and position in hex. Hex is used since decimal digits used up too much time. It took too long to send them. And the ADC does 860 samples per second, so each line has to be sent in a short amount of time. Okay, now for the results. By the way, the watt balance should be called the Kibble balance, but I will keep calling it watt balance. The watt balance measures something called BL, flux integral, where B is the magnetic flux density and L is the length of the wire in the coil, or both coils in this system. There are two BLs, the BL found when the balance works in velocity mode and the BL when the balance works in force mode. Earlier when I was showing it, the rocking back and forth, that's velocity mode. As near as I can tell from the documents about the watt balance, after 2019 these two BLs should be the same value. So if my two values are near the same, then my watt balance should be in good shape. The BL from velocity mode is the slope of the line on this plot. After 30 cycles are averaged together. The BLV is 36.27 volt seconds per meter. Here's a plot of just one cycle of 1,270 points. Note how noisy the signal is. I think most of this noise is the interference pattern of the line laser. If I average the 30 cycles but offset each by a few points, then the cyclic nature of this noise goes down. When I shine one of these line lasers at the wall, you can see a series of tiny dots along the length of the line, so I think that's just the way those things work. Okay, the BL force measurement is not so interesting to look at, so I don't have any pictures of this except my scribbled sheet of calculations. I just measure the voltage across a resistor with a weight on the balance. In this mode, the balance works like a laboratory balance. I use a stack of 3 pennies and a stack of 6 pennies. Place 3 over one coil, adjust the voltage in the coil so the beam balances, then place 6 pennies over the other coil. Reverse the current and balance the beam again. I did 3 runs of each and averaged the results, which results in a BL force of 36.22. By the way, I'm using a little gram scale to weigh the pennies since I want to verify the balance is working correctly. It's not really cheating. So this document shows the formulas for the flux integrals, and it appears my balance is 0.14% accurate. Note the mass formula. The balance can now be used to weigh light objects. The mass formula determines mass from volts, resistance, or resistance is actually current is used in the formula, but current is determined by volts divided by resistance. So the real watt balance has very precise measures for resistance. Well, the other two items are velocity and gravity. Determining the mass using this device was one of the goals of the 2019 redefinition of the SI base units project.